Have you heard of these terms? Viscosity, elasticity, surface tension, anywhere?
Viscosity, sir, I heard it from your friction video, but that's about it.
Yeah. So what is viscosity? Actually, now you might have seen, like when you're trying to pour honey, it's difficult, right? To pour honey to a container. So there's some resistance within the fluid against motion, right? So there's some resistance against the motion of a particular object that you put into a fluid, right? So there's friction in fluids also. That is what we refer to as what? Viscosity, right? So now you know on a surface, when you're trying to move an object on a surface, what do we have? When you're trying to move an object on a surface, there's friction, right? Opposing your movement. But in fluids, we have another resistance that is called what? Viscosity. So now, you know, for example, honey has what? The high viscosity. Have you all noticed that? When you're trying to pour honey into a container, it's kind of difficult, right? Container, it's difficult, right? But when you're trying to pour water, it's not that hard. So that means honey has a greater viscosity, a resistance to movement, right? And have you all noticed that when you increase the temperature, that means when you heat up the honey, it's easier to pour the honey. Have you all noticed that?
Yeah, so that means that it's flowing faster because of the temperature. So temperature is
When
affecting.
the temperatures are very good. So when you increase the temperature, the viscosity goes down, right? So today our topic is about viscosity. So we will cover viscosity, then we go on to what? Talking about surface tension, or we can start with elasticity, does not matter. So shall we start then? I hope everybody. So then, now if you look at this, properties of matter. Now just observe how difficult it is to pour honey, right? It's highly viscous. You might have heard of viscous fluids. And you can see a spring here that we can stretch. So there's this topic of elasticity, right? Elasticity of material, the ability to stretch a particular material, right? And then surface tension. Because of surface tension, these insects, they can move on water surfaces, right? You've seen this in water films that these insects can move around, right? So viscosity. Now see, honey has a high viscosity value, and that is why it's difficult to pour the honey. So it takes a greater amount of time to what? Pour the honey, right? But if you think about water, water has a relatively low viscosity value. Therefore, it's easy to what? Pour water. And it takes a lower amount of time to pour a particular amount of water. So now you can see even when stirring, it's the same thing, right? This resistance to movement is what we call viscosity. There's this resistance to movement, right? So now if you look at this syrup, it has high viscosity. It's viscous. So it's very difficult to stir it. But if you compare that to water, it's easy to stir water, right? So that shows us that water has a lower viscosity as opposed to the syrup. And now we'll be talking about a particular law that's known as Stokes' law, right? In Stokes' law, we talk about the movement of a sphere, right? So now, if we just release a sphere in water, that sphere is going to move through water, and we are going to see the behavior of that movement, right? So now, I hope you all can answer these questions. So, what is streamlined motion? How is it different from turbulent motion? Yeah, answers are invited. You all can freely learn, right? That's the process of learning, to be very free, right? Study with freedom, right? So I can talk about anything you all want, right? Ask any question you all want. And so we are starting with what is streamlined motion, right? How is it different from turbulent motion? Any ideas?
So I'm not very familiar, but like streamline motion, is it like straight? And turbulent is very shaky?
Yeah, so we are coming close. So now let's see. Streamline, right? It shows that the motion is uniform, orderly, right? Streamlined motion. Now, actually, when the speed of fluid motion, right? When the speed of fluid motion reduces, we see streamlined motion. right? Now, have you all seen water flowing from a tap, right? So this is the opening of the tap. So water flows more calmly, right? More calmly when the tap is open a little, right? But it's chaotic when the tap is opened wide. You know that, right? It's chaotic motion of the fluid. Have you all seen these things? When you open the tap a little bit, you can see streamlined motion, right? Something like that, okay? But when you completely open the tap, what can you see? When you completely open the tap, there's a very violent motion, turbulent motion. There is no order, right? There's disorder. There is chaos. So now, in streamlined motion, the flow of the fluid is uniform and orderly. So what do you mean by uniform? It's regular, right? And it's orderly. There's a particular order about the motion. The velocity of a particle that passes through some point remains the same in terms of magnitude as well as direction, or changes in a regular pattern. So it's like this. In streamlined motion, which I think I discussed in fluid dynamics, in streamlined motion, for example, let's observe this. You can see a particular order. The particles move like so. There's a particular order, right? So the velocity of a particle that passes through some point remains the same in terms of magnitude and direction. So let's say this is the point A that we're considering, that we're interested in. So the direction of that particle and the speed of that particle, right, or the velocity at that particular point of the particle remains the same, right? Or there's also this special occasion that we talk about, this ability to change in a regular pattern. That means the velocity of the particles passing through that particular point can change in a particular rhythmic pattern, in a particular regular pattern with order. As long as there's order, we call that motion streamlined motion. Is that okay? Everybody understood?
Yes, understood.
Yeah, sir.
Okay, perfect. So the path of a fluid molecule in a streamlined flow is what? A streamline, right? The path of a fluid molecule. Now see, suppose it's a streamlined motion. This is the particular path of that fluid molecule. This is the fluid molecule that we are interested in, and that is the movement of that fluid molecule in a streamline, right? That is what we call a streamline, the path of the movement of what? A fluid particle in a streamlined flow is known as a streamline. And now something very important is, now if you draw a particular streamline like that, and if you mark a particular point like so, let's say point A, and if you draw a tangent to that point, what do you observe? Actually, when you draw a tangent to a point A that is present in a streamline, we get the velocity of the particle at that particular point, right? So there's a streamline. The streamline shows the path of the movement of the fluid molecules. So if you mark a particular point A, and then if you draw a tangent at that point A, right, then you can see the direction of what? The fluid particle that's exhibiting a streamlined flow. Is that clear? Right? So,
Yeah, okay.
okay, and then I just want you all to see something very important. Can streamlines ever cross each other?
No,
Is that
they
a
cannot
possibility?
cross each other. It's like they are
Very
having
good.
their own track and they are like sliding without bumping into each other. It's like ordered,
Okay,
right?
it's ordered, but my question really is now, can they cross each other? Why not? Why is it not possible for them to cross each other? Why can't streamlines cross each other?
Mm,
If you
if they
if you look
cross
at it,
each other, then they have to go in
yeah,
two directions at once, right? if they have to cross each
Exactly.
other.
Brilliant. Brilliant. So a single particle cannot have two different directions at the same time, right? It's impossible, right? You can't have two different directions at the same time, two different directions of movement at the same time. It's impossible, right? So that is why we say streamlines cannot cross each other. So in turbulent flow, the flow of the fluid is irregular, is disorderly, just like when you open the type wide, right? There's chaotic motion. The voltage spills up, right? It's chaotic. The velocity of a fluid particle passing a particular point changes in magnitude and direction frequently, right? There's a frequent change in what? The velocity. That's clear. Because it's chaotic, you can't expect a single molecule to be having the same velocity, right? Now see, let's think of a point A. Think of a point A. Think of a fluid molecule that's reaching this point A. Okay, let's say fluid molecule 1 has a particular velocity like so when it reaches point A. Let's say we consider the second molecule. Okay, that second molecule is going to have a different direction. Same point, right? So all these fluid molecules are going to the same point of interest. For example, think of a tube, right? You can think of a tube and think of the movement of a fluid in the tube and mark a particular point A. Now, if ever the motion is turbulent, what happens? The velocity of the particles passing through that considered point is always going to change with time, right? It's not. And also, the way it changes with time is disorderly. There is no pattern, there's no order, there's only chaos, right? I hope you all understand the difference between what? Turbulent flow and streamlined flow, right? Okay.
Yes, sir.
Yes,
Right,
understood.
good. Okay, so now we're going to see what laminar flow is. What is this laminar flow? When the fluid flows as layers, the fluid is flowing as layers. The fluid exhibits what we call laminar flow. Exhibits laminar flow. So when the fluid flows as layers, we see what? Laminar flow. A layered flow of what? Fluids. So basically something like this. So we have layers that move, right? Layer wise, the fluid moves. The velocity of every fluid particle in a considered streamline is the same. What do you mean by that? That means if you consider a particular layer, right? And think about a particular streamline in that layer, what can you say? A particular streamline in that layer, right? When you consider a particular streamline in that layer, every fluid particle in that considered streamline, so this is a streamline, so every considered fluid particle in the streamline has the same velocity, right? So velocity of fluid particles in different streamlines can be different. We can have many layers, right? We can have many fluid layers. So we can have many fluid layers like that are going on top of each other. Now, when you draw the streamlines in those layers, think about the top streamline like so, and then the bottom streamline like that. And then what happens? The velocity keeps on decreasing. I'll tell you why. I'll tell you why the velocity keeps on decreasing, but just observe this. Velocity of fluid particles in different streamlines can be different. See, this is streamline 2, this is streamline 1. The velocity of fluid particles within streamline 1 is the same, but when you consider particles of different streamlines 1 and 2, what can you say? the velocities are different, right? The velocities are different. Okay, I hope you all understood that section as well. So now I need to draw some things. So I need some space. Let me see if I can make this smaller. Right. Now, let's consider a laminar flow, right? That happens on a, let's say, a horizontal plate or something, right? So let's say we're talking about laminar flow that happens in what? In a horizontal plate. In a horizontal plate. Laminar flow that happens in a horizontal plate. Now just think of the plate. This is the plate. Now, let's think of fluid layers of interest. Let's say I'm drawing a particular fluid layer like that. Right? I'm drawing a particular fluid layer like that. And then on top of that fluid layer, I'm going to draw another layer. Now what happens? When I draw another layer on top of that fluid layer, and then another one on top of it, right? Sorry. So now, let's say thinking about a scenario where you are having a block of some kind, and then there's a very thin film of liquid. So here we have a block of some kind, right? A particular block. And then there's a thin film of liquid. And then, of course, we have the plate, right? We have the plate. It's a solid plate. Solid plate. Now tell me, if I drag this with a particular velocity v, the topmost layer is also going to drag itself at that particular velocity, right? So the layer just below the block, the layer just below the block, that's what I've highlighted here. The layer just below the block is going to have what? The velocity of the block. Okay? And if you think about the layer just touching the solid surface, just touching the solid surface, that particular layer of liquid just touching the solid plate surface is going to have a velocity of 0 if the solid plate is at rest, right? So the solid plate is at rest. Therefore, whatever the fluid layer that is in contact with the solid plate is gonna be what? At rest. But the top layer of the fluid that is connected with the block is going to have the velocity of the block itself, right? So now I'm gonna mark the velocity here as v2 and the velocity here as v1. Now you can see here that v2 is greater than v1. And then my question is why, right? Why do you think velocity v2 is greater than v1? What is the possible reason for v2 to be greater than v1, right? What would be the case? Now, if you closely observe this, right? Think about this layer, the top layer, and then the bottom layer, right? The bottom layer like that. So then when this moves with a particular velocity v2, and then when this moves with a particular velocity v1, you know that you have talked about relative motion, right? So when the top layer that I marked here moves faster than the bottom layer, there's going to be relative motion, right? There's going to be relative motion. And then you know for sure that when layer 2 tries to slide in front, right? When it's trying to move against layer 2, when this tries to move against layer 2, what happens? There is resistance to the movement of the top layer. So there's a frictional force that the top layer experiences, right? There's a frictional force the top layer experiences. You know, we talk about forces always occurring as what? Pairs, right? Forces always occur as pairs. Now, when you go and push on the wall pushes back upon you. Newton's third law, right? For every force that you apply, right, there's an equal and opposite force. That means for every force that you apply, there's a force equal in magnitude, but opposite in direction, acting on two separate objects or entities,
So
right?
that's why the upper layer is sliding faster while still dragging the lower layer slightly, right? Just like the Newton's third
Exactly.
law.
Brilliant.
Okay.
Brilliant thinking. That's what I want. Perfect,
Yes.
right?
Okay.
So
Thank you.
now there is going to be an external unbalanced force acting forward on the bottom layer, right? Because forces always occur in pairs. Ne? So when the top layer is trying to slide against the bottom layer, the top layer is pushed backwards, right? But then the second layer is being pushed forward. So the bottom layer is going to get an acceleration, a movement, a velocity, right? Now I think it's clear why the entire thing moves. But the thing is, what happens to the velocity distribution as you go down to the bottom? Can the bottom layer move? No. Why? The bottommost layer that I highlighted here, the bottommost layer, is attached to the solid plate. When the bottommost layer is attached to the solid plate, what happens? The velocity is zero because the solid plate is not moving anywhere. So now we are going to come on to the tangential stress and the velocity gradient topic, right? Okay. So I hope you all don't have any doubts up to this point so that I can continue. And
Yeah,
the
sir,
note
it
will,
was.
okay, great. So I'm going to mention something else. Now, think about a cylindrical tube, right? Streamline motion. No, let's think about laminar motion. Sorry. So laminar flow that takes place in what? In a cylindrical tube. Laminar flow that takes place in a cylindrical tube. So what do you see? When you think about a cylindrical tube like that, so if I draw the fluid layers, what's the movement? Can you see fluid layers are like that? Right? So we have cylindrical fluid layers, right? We have cylindrical fluid layers like so.
So the layer in the innermost part is going to have more velocity?
Exactly, brilliant. Now see, y'all are thinking. This is what makes me happy, right? I like to see ideas coming out like that. And that's a very good conclusion. Why? Because you think about this, if I draw a line like that, let's say from A to B, if I draw a line from A to B like that, what do I see? Yeah, I see that the velocity is maximum, as Amaya said, the velocity is maximum, but at the center. Because if you think about the fluid that's touching the surface, what can you say? The fluid that's touching the surface has a velocity of zero because the surface is at rest. The solid cylinder is at rest, right? So then, what do you see? But the pattern of velocity distribution has to be something like this, where the velocity becomes zero here and it slowly increases. That's very intuitive. Feel it, right? Now, think about this. What is the pattern that you observe here? The pattern that you observe here is something like this. You know, when you think about the block that moves on top of this particular liquid layer, this is attached to the surface. This is a solid surface. I use a different color. Solid surface. All right, solid surface. Okay, so here, you know, the velocity is 0. Here, the velocity of the block that's moving on top of the liquid is v. Therefore, the fluid layer just below the block is v. So the velocity distribution is going to be something like so, right? So this is laminar flow. All right. Now, is everyone okay up to this point? You can ask any question you all like. I'm sorry I can't see the chat, so you can, if someone has asked a question, please tell me that, right? You can forward that to me, to WhatsApp or something, or I will intervene. Just let me know, right? Okay.
Yes, sir.
So
No questions yet.
no questions yet. That means it's absolutely clear, right? Absolutely clear. Crystal
Yes,
clear, I
sir.
hope.
Crystal clear for now.
Crystal. As clear as it gets, no? Right. Okay, so this is the velocity distribution. All right. So the velocity distribution, and we saw the velocity distribution here as well, on this side. So y'all can do the note taking at home, I hope, to save time, right?
Yes, sir.
So,
It's
okay,
like
great.
reminding me how the blood is flowing in the arteries. Like the cells
Exactly,
near
we
the
did that
wall is
lesson, right?
moving slower.
Ooh, biology.
Yeah. So it comes up, see,
Biology and
viscous.
physics.
Yeah,
Yeah,
these guys
physics
for releases.
principles applying in the biological systems.
Yeah, exactly,
It's
right?
everywhere.
It's everywhere. So you have to be able to relate those subjects together. That's the holistic perspective that
Mm.
we had, right? Remember when we
This
discussed
is
about circulation, I mentioned
awesome.
about viscosity, right?
Hmm.
And also about heart diseases that are there. We have to talk about how to reduce the viscosity of blood, how to improve the movement, and these cardiac issues that we have, right? We can use these physics principles to counter those issues, right? Even the drugs that they make are are made to what? Solve these issues. Okay? Right.
Oh, so
So
all these sciences go hand in hand.
all of it goes hand in hand, exactly. Right. So we need sometimes drugs to what? Reduce the viscosity of blood. Because if it's viscous, the flow is going to reduce. No? The blood flow does not happen properly. Should not be too thick. So then we have to have drugs to reduce the viscosity. So
So
if you're
that's for
interested,
people with low pressure.
yeah, so we'll be talking about that low pressure
Okay.
issues and all that, and the heart problems and everything, right? We'll be talking about. Okay?
Okay.
Right. Great. So, and then now we're going to talk about tangential stress and what? Velocity gradient. Now, what is this? I think we already talked about this a little bit. Okay, so if I draw a particular layer like this, and then another layer, what can we see? There's a particular height difference, delta H. Now, suppose this top layer has a velocity of what? V plus delta V. And suppose the bottom layer has a velocity of what? V. Now, when the top layer is trying to slide over the bottom layer, now you can see the top layer has a greater velocity than the bottom layer. Then there's going to be relative motion. Then there's going to be friction. So as I mentioned, now there's going to be a backward force on the top layer. And the bottom layer is going to experience a forward push, a forward force that moves the bottom layer. Now, if you think about this, what can we say? Can you see the force occurs along the area? The force occurs along the area, right? So what happens if the force occurs along the area? This is what we define as a tangential pressure or a tangential stress. It's along the area. Now, you know what pressure normally is, right? So when you have a force that is perpendicular to a particular area, we define it as what? Pressure. But now here, the force is occurring what? Parallel, right? Along the area. And then we define a particular pressure called shear, or we say tangential stress, right? So what is tangential stress? F over A is defined as what? Tangential stress. Tangential stress, right? So it's the force that occurs on a unit area. This force that occurs on a unit area is along the area. Okay. And now, if you consider
Sir,
these two fluid layers, what can we say?
sir,
If you consider these two fluid layers, there's a particular height difference between those fluid layers.
Sir, someone's
And it
calling you.
really,
Yeah.
sir, excuse me,
yeah,
sir.
yeah, sure. Please do ask the question.
Um, so what's the difference between tangential stress and just normal pressure?
Yeah, tangential is along the surface. Right now, normally when you consider a particular area, right? If you apply a force perpendicular to it, you can see the force is perpendicular to that particular area considered, right? But here, what do you observe? The force occurs along that area. Is that clear? Understood. It's occurring along it. It's like we're sliding it. It's a sliding pressure. It's like you're pushing it, just like books, no?
Oh,
When
okay,
books,
sir.
you have seen, right? When the pages are kind of pushed to one side. Have you all seen that?
Yeah.
Textbooks that are very big. Can I know your name?
Minuku, sir.
Did I teach you in
Yeah,
St. Peter's?
so you actually came to my school for like a small seminar?
Oh, you're
Sir,
the
they
one
are
with
the
glass.
St. Peter's ones, right?
Yeah.
Yeah. Okay. Great. What about the others? I don't know. I hope they can join the next session, right? So, Minika, you are the one who was in the middle row and I talked to you, right?
Yeah, sir, yeah.
And I asked your name. I remember. Now I remember.
Oh, okay. It's pretty cool.
Yeah. Great. So, I'm happy that you joined. So, you can ask any question and the people around are very friendly, right?
Okay, sir.
You can chat with them. They're very interactive, right? So, yeah. And I'm happy that you're talking. So, the force is what? Along the area. And that's what we call what? Tangential stress. And now we say that this tangential stress, F over A, the tangential stress F over A is proportional to what? The velocity gradient. The velocity gradient. What's the velocity gradient? V plus delta V minus V is the velocity difference, right? V plus delta V is the top velocity. And at the bottom layer, we have velocity of V. Then tell me, what's the velocity difference?
Delta
Delta
V?
V, right? Delta V, exactly. Then what's the velocity gradient? That velocity difference we divide by the height difference. This is what we call what? Velocity gradient, right? This is the velocity gradient. So this is the tangential stress. Tangential stress. And now, as always, there's a particular constant, right, that we put in. You know that. There's a particular constant we put in. So to make it an equation. So we can say then F over A is equal to what? Some kind of a constant, but this constant is special. That's called eta, multiplied by what? Delta V over delta H. This delta V over delta H, we know that is what? The velocity gradient, right? That's the velocity gradient. What is eta? Eta is defined as what? Coefficient of what? Viscosity. Eta is defined as coefficient of viscosity. It depends upon the material, whether it be honey or whether it's water, whatnot, right? So I hope that's clear.
So it's
And
kind of like
eta,
friction.
yeah, it's kind of like friction, exactly. We're talking about friction in fluids, right, Amaya? Talking about friction in fluids. Right, so then what's eta? Coefficient of what? Viscosity. This depends on what? Temperature. Depends on temperature. And also what? And the type of the fluid. And the type of the fluid. So eta depends upon the temperature and also the type of the fluid. Okay. And then I can say, now, once I look at the equation, F over A is equal to eta into delta V over delta H. Now, I can isolate eta, right? What do I get then? I get F over A into what? Delta V over delta H. And that helps us to define what? Viscosity. Is that clear? That helps us to define viscosity. Are you all okay up to this point? Is the connection okay? I don't know with this weather condition is prevailing in the
For me,
country.
it's all right, sir.
It's all right, right? So
Yes.
some of y'all can manage, but I feel bad for the others. They may be having some connection issues. I'm getting some messages telling that they are not able to join. They are having a lot of connection issues. Never mind, I'm recording. Is it still recording? It's recording, right? Others can access it, I
Yeah,
hope.
yep.
Right. Right. Okay, then, now when I isolate eta, can you see F over A into delta V over delta H? So what can we say then? We can say, what is eta? We can define eta like this. Coefficient of viscosity is what? Defined as what? Defined as the tangential force. Tangential force on a unit area. On a unit area. Right? A tangential force on a unit area under what? Under a unit velocity. Under a unit velocity gradient. Under a unit velocity gradient. Is that clear? Right? It's defined as the tangential force that acts on a unit area under a unit velocity gradient. Considering what? Considering streamline motion. Streamline motion. Okay? So when you make all these 1 and 1, eta becomes equal to F. That's the definition. All right. So, streamline. Sorry.
So it's like measuring the fluid's resistance to sliding in the laminar flow. Like the more viscous, the more harder it is to make that layers move.
Yeah, exactly. Very good. It's harder to move, right? It's resistance, exactly. Now, so we talk about Newton's law of what? Viscosity. That's what we just talked about earlier, right? We talked about Newton's law of viscosity, where I said F over A is proportional to what? The velocity gradient. And then I get what? F over A equals eta into delta V over delta H, right? Okay. Now, I told you it depends on temperature, but I forgot to write this here. How does it depend on temperature? When the temperature increases, what happens to viscosity? When the temperature increases?
That one
Decreases.
Yeah, very good. Viscosity
decreases.
Decreases.
decreases. Exactly. Stokes' law. Actually, let's start with that. Now, when you consider a particular sphere, let's say a solid sphere, right? Let's think about a solid sphere. Is it recording? It is, right?
Yeah,
Yes.
sir. Yeah.
Suppose there is a solid sphere. And then, suppose I'm going to release it at a point, right? I'm going to release it at a point. Suppose I dip it like so and release it. What's the velocity? V equals 0. I'm just going to release it, right? It's at rest. This is a mechanics part. It's lovely. I'm going to just release it from rest. Okay. Now, this particular sphere of interest, right, has a particular radius. Let's say R. Okay. And suppose this particular sphere is made up of a material of a particular density value. Let's say it's made up of what? Density rho. Now, why am I telling that this sphere is a solid sphere? Because it's fully filled with material, right? If it's a cavity sphere, inside is empty. So when you define density for a cavity sphere, you're talking about net density, right? Overall density. But when you talk about the density of a solid sphere, you are talking about the density itself, right? Okay. Now listen, everybody. I'm going to release this now. What happens when I release the sphere? What's going to happen? Well, the velocity initially is 0. Now you have to think about the forces occurring on the sphere. What are the forces occurring on the sphere? Weight, mg. Do you agree? Of course, the weight is there, right?
Yes.
Weight is of course.
Yeah.
And there's upthrust. So Maya might have learned in all levels about upthrust.
Yep.
Don't worry. Others know what upthrust is, right? So basically, when you have a particular object that is sunk in a fluid, the volume sunk multiplied by the density of the surrounding liquid, let's call it raw liquid, multiplied by what? Gravity, you see what? Upthrust, right? So even 2027 students who are watching this, for them even, just get an idea. You'll be learning about upthrust deeply, but it's the volume sunk, the volume of the object that's sunk in the fluid, multiplied by what? The density of the surrounding fluid, multiplied by gravity, gives you the upthrust that the fluid exerts upon the sphere. So at this moment, isn't upthrust there? Yes, of course. Upthrust is there, right? So now suppose this object is heavy. What's going to happen to that? It's going to go down, right? Right? If the density of this object is greater, then what? The surrounding fluid's density, it's going to go down. It's going to sink. So can someone tell me what's the external unbalanced force occurring at this instant?
mg.
Minus u. mg minus u. Because upthrust is acting upwards, weight is acting downwards. So what's the resultant force at this instance? mg minus u, right? So we will talk about situation 1. I'll call this situation 1. So when you look at situation 1, what can we say? mg minus u is going to be the resultant force. Now, you know F equals ma, right? F equals ma. So when there's a particular mass m that has an acceleration a, we say the external unbalanced force causing that acceleration a is F. Is the external unbalanced force acting on an object in a particular direction that gives a particular mass m a particular acceleration, right? So now you can see the resultant force is acting downwards, right? It's acting downwards. This resultant force, isn't it equal to the mass of this object, this sphere, multiplied by the acceleration that it's going to have at that instant, right?
It's
So this,
equal.
yeah, exactly. So this is going to have a particular acceleration, all right? So mg minus u equals ma, okay? So mg minus u equals ma, mass into acceleration. So now you can see what is the initial acceleration of the system. A equals what? Mg minus u over m, right? A equals mg minus u over m. But I'm going to expand upon this. I can write the mass of the sphere in terms of its volume and its density, right? I told you that the object is going to have a density of rho. This object has a density of rho. Okay, so what is going to be the mass of this object? Volume multiplied by the density of the object. What's the volume of the object? 4/3 pi r cube multiplied by rho, right? Now tell me, what is upthrust? Volume of the object that's sunk multiplied by the density of the liquid multiplied by what? Sorry. So that's upthrust, yeah, multiplied by gravity. That's upthrust. But what is the weight mg? Multiplied by g, right? Mass multiplied by gravity gives you the weight. So what's the upthrust then? B rho liquid g. But what's the volume? 4/3 pi r cube rho liquid g. All right, now I can substitute it here. Let's do it. Acceleration is equal to what? Mg minus u over m. What's m? 4/3 pi r cube rho g. That's mg minus upthrust 4/3 pi r cube rho liquid g. Now divided by what? What's the mass? The mass is going to be 4/3 pi r cube rho. That's going to be the mass. So you can divide some terms, right? So you can divide this. Cancels off. So what do you get then? I can take g out. Multiply by what? Rho minus rho liquid. And I can divide it by what? Rho itself. Okay? Right. I hope that's clear. Did everybody catch up with this?
Yes, sir, that was nice.
Yes, it was okay.
Right, great. Then, now tell me, if there is an acceleration, what should there be? If there's an acceleration, there is what? An increase in the velocity. As long as there's an acceleration, the velocity is going to increase in that direction, for sure, right? So what's going to happen then? Will it forever be at rest now? No. It has an acceleration, therefore it's going to accelerate downwards. It's going to increase its velocity downwards. So the moment it gains a velocity, there's another problem now. What's the problem? The moment it gains a velocity, there is what? Friction. We just talked about it now, right? The moment it gains a velocity, there's what? Friction. Resistance against the movement, right? This fluid layers, now when the sphere is going to go down through the fluid, what happens? There's going to be resistance against this motion, right? Okay. Then now a new component comes in. Velocity is v now. Of course, there's what? Upthrust u acting upwards. Weight is mg downwards. Now there's an additional force acting upwards, right? Opposing your movement. What's that additional force opposing your movement? The viscous force, right? The viscous force opposes your movement. So here we go. This is going to be the viscous force that's going to be acting upwards. This is the frictional force. Why? Because there's a velocity. So we say this viscous force that's occurring on the sphere. So viscous force occurring on the sphere. Viscous force acting on the sphere. It is proportional to what? The radius of the sphere. But is it directly proportional? No. To some power x. We don't know, right? And this viscous force is also proportional to the velocity to some power. This viscous force is also proportional to viscosity into some power. So we can take all the proportionalities into one connection now, and then we can see viscous force is proportional to what? R to the power x, v to the power y, e to the power z. Now what you have to do at home is you can put a constant, right? R to the power x, v to the power y, e to the power z. And you can find the values of x, y, and z. I want you all to try this at home. If there are any difficulties, just let me know. Y and z. When you do solve this, you eventually find out that the viscous force can be written as K R1 V1. Sorry. Yeah, R1 V1 eta 1. So then X, Y, Z are all going to be what? 1. Right? So then we get F equals what? What's K? K is a constant, but they have found out that constant to be equal to what? 6 pi. So we get what? F equals 6 pi eta R V. What's V? The velocity. V is the velocity. What's eta? Coefficient of what? Viscosity. What's F? The viscous force. The viscous force. All right? Okay. Now that we know about this, we can see a connection now. Now I will just copy the same thing down and let's explore now. Let's explore. What is the acceleration now? What is the resultant force now? Well, the resultant force now is going to be what? mg minus u minus f. That resultant force is equal to ma. Right? So then, can you tell me what is the acceleration equal to? You just have to divide by the mass m, right? On all sides. Then what do you get? mg minus upthrust minus the viscous force divided by the mass m gives you the acceleration a. All right? Now tell me, what's the mass we found out? Actually, I'm not interested in putting the volumes again because I'm not interested in that result, right? We will put the volumes back again in a particular critical situation known as the terminal velocity. Before coming to that, I want to address one idea. Can you see initially the acceleration was mg minus u divided by m? But now the acceleration is what? Mg minus u minus f over m, right? Mg minus u minus f over m. And that is going to be the acceleration that you have now. Okay? Now what can we say? Aren't you reducing the resultant force now
Yes,
compared to the
so
initial
the
situation?
acceleration is also going to get less.
Exactly. It's
And
going to
the
get less. Velocity is a different matter, Maya. I'm going to go into that, right? So it's different. We are going to argue about that in a while, right? So anyway, this is the maximum acceleration possible, right? Because can you go beyond this? No, right? Because as you go down, there's going to be viscous force acting upwards, which essentially reduces your resultant force and thereby the resultant acceleration. So stick with me there. I hope everybody's fine, right? Now tell me, there is an acceleration, okay? But that acceleration is decreasing, isn't it? There is an acceleration, listen very carefully. There's an acceleration, but that acceleration is decreasing, right? Yeah, which means what? If the acceleration is decreasing, what can we say? Does that mean that the velocity is decreasing? Does that mean that the velocity is decreasing?
No.
No, no. The rate at which the velocity increases decreases. Remember, what's acceleration? Rate of change of velocity. If the acceleration decreases, the rate by which the velocity increases decreases. Okay? That is the core idea you should have. Because as long as there's an acceleration, you are going to increase your velocity. That is the very meaning of acceleration, right? But as the acceleration decreases, the rate at which your velocity increases actually decreases. That is the thing that's happening. So you can see here, even though the viscous force is acting upwards, your velocity keeps on increasing. What happens when the velocity increases? So let's catch up with the things that we have talked about. So let's write down the things, right? So as the viscous force increases, when the velocity increases due to the downward acceleration, what can we say?
The upward resistance grows, right? Which is reducing
Yeah.
the net downward force.
As the viscous force increases when the velocity increases due to the downward acceleration, the net, as Rita said, the net downward force decreases, right? Net downward force decreases. Very good.
So the acceleration decreases as the sphere speeds up, but the velocity still keeps increasing, but
Brilliant.
just slowly.
Exactly. Yeah. So therefore, what can we say? Therefore, the acceleration decreases. But how does it decrease?
While the
How does the
velocity
acceleration decrease?
increasing, but slowly, more
The
slowly.
acceleration decreases because the resultant force decreases, right? So, but as there's still an acceleration, but as there is still an acceleration, what happens? Velocity keeps on increasing. Velocity keeps on increasing. But the rate at which the velocity increases decreases, right? The rate at which velocity increases decreases. All right? Okay. Now you all have a good idea. Now, what will happen eventually? Now you see mg minus upthrust minus the viscous force divided by the mass m gives you the acceleration downwards a. Okay,
So eventually,
what's going to
So
happen eventually?
does like with depth the viscous force increase or anything?
Yeah, it's increasing. That's what we discussed, Amaya. It increases, but what
So
happens is
velocity is
it
gonna get
keeps on
constant?
increase. Yeah, very good. Eventually, it reaches a constant value. How? Let's go into it. What happens actually is f keeps on increasing. F keeps on increasing. Eventually, what will happen? Because yeah, the acceleration keeps on decreasing, all right, but with that, the velocity keeps on increasing, but reluctantly, right? But the core idea is
acceleration.
it. Yeah.
So
Sorry.
when the spear is released, the weight is pulling it down, and the upthrust is pushing it up, pushes up, right? So since the
Yeah.
weight is big, the net force is downward, and the spear is accelerating downward. No.
Yeah. True. But the thing really is the downward force mg
So,
minus u minus f.
so isn't this just terminal velocity? Isn't that what happens
Yeah.
in the end?
Exactly, Vinuka. We are going to come to terminal velocity. So now I tell you. Now let's start again. Mg minus u minus f is the resultant force, right? Is everybody okay with that? That's
Yes.
perfect, right?
Yeah,
Now
yeah.
what happens is, does mg minus u change? No.
No.
But the viscous force upwards increases. So eventually what will happen? Eventually, mg minus u becomes equal to f, right? Yeah, it can become equal to f. So what happens then? Then, as Minuka said, we reach what we call what? Terminal velocity. It's a constant velocity, right? So
So the
eventually,
acceleration becomes zero, and the spear is moving at the terminal
exactly,
velocity.
yeah,
Okay.
exactly, right? Acceleration becomes zero. So here we can see all the forces are balanced now. Mg, upthrust, and then the viscous force F. So you can see U plus F equals what? Mg, terminal velocity. So the velocity here we are getting is terminal velocity. This is the terminal velocity, right? Terminal velocity. Now, after that, is there any reason to change the terminal velocity? Is there any reason to change it?
No.
No, it will
The mass
continue to be
isn't gonna get
consistent.
bigger, so
No, the mass is not going to change. And so, as the moment U plus F becomes equal to mg, there's nothing that causes a change in what? The velocity. Velocity is not going to increase anymore, therefore the viscous force will not increase anymore, right? That's the fun part. As the velocity is constant, the viscous force does not change. So now viscous force has become a constant. Everything is a constant now. Then U plus F equals mg. Then what happens? There's a terminal velocity. That is the idea. But now listen carefully. Pay a lot of attention to this, right? We are going to derive an equation. Now, you know U plus F equals mg. What is upthrust? 4/3 pi r cube rho liquid g plus viscous force 6 pi r eta vt. What's vt? Terminal velocity. That's equal to what? Weight mg, right? Weight mg. So what's the weight mg? 4/3 pi r cube rho object, density of the object, multiplied by gravity. Now I can take 6 pi r eta vt to one side, right? And that is equal to what? 4/3 pi r cube rho g minus 4/3 pi r cube what? Rho liquid g. Now I can simplify this, right? I can simplify this. How can I simplify this? What I can do is I can divide by 2. What happens if I divide by 2? This
Plus
becomes 2,
6.
this becomes 2, this becomes 3. And what I can do after that is I can multiply the entire equation by 3. Multiply the entire equation by 3. 3 times this, right? Then solve these questions mentally. What happens when you multiply by 3? And whatever you can cancel off, let's cancel off, right? See, I can cancel off the radius here, pi here, right? And then Is that all I can cancel? Again, this becomes r squared. This becomes r squared, right? Yeah. Now I'm going to multiply the entire equation by 3. What do you get then? 3 times this equation. So what do you get? 3 times 3, 9. So 9 eta vt equals what? 3 times 2, 6. Right? So you get 6 there. We are on the right track, right? So we are multiplying by 3. But the problem is when you multiply by 3, you don't have to take it that way. When you multiply this term by 3, what happens? This 3 and this 3 cancels off, right? So you don't have to think about the 6 there. This 3 and this 3 cancels off. Then what do you get? 2 r squared rho g minus 2r squared rho liquid g. Right? Now we can simplify this furthermore. You can divide by 9 eta, right? Divide the entire equation by 9 eta. 9 eta. So don't just write pages of simplifications, no? Well, you can do this thing very easily. So what is the terminal velocity equal to then? Yeah? Terminal velocity is equal to what? You can see,
Excellent.
I can take some common factors out. 2r squared over eta 9, can take it out, right? And I can take g out, right? Yes. And then I get what? Rho minus what? Rho liquid. Is that clear? So this is very
Multiplied by
convenient. Yeah, gravity is there anyway, right? It's a very simple equation. But remember, we proved this assuming what? Considering the sphere solid sphere. Considering the sphere to be what? A solid sphere. Clear? If it's cavity, you have to think about the net density then. You can think about density. You can apply this equation as well to cavity sphere. Then the definition of your density has to be a net density. Is that clear? This rho has to be a net density, all right? Okay, I hope everybody's fine up to that extent.
Yes.
yes. Yeah.
So I was
I
just
want
wondering,
Yeah,
this is assuming it's a uniform body of water, right? So in like a practical case, like a
yeah,
large
exactly.
body of water, the density changes, right?
Yeah, with the high, like this consistency has to be there. So otherwise we can't prove these equations, no, Vinika, right? So the flow is also very steady, it's not chaotic, and this object is not rotating around, So
Yeah.
and the velocity is not that high, no? Also,
So
the velocity is too high.
what
Sorry.
if the sphere was also rotating? Wouldn't you have to like calculate for like the tangential acceleration and stuff?
Yeah, it's going to be very complex then. Within your field, we can't solve those questions. There are so many variables, no? Now, for
Yeah,
example, multivariate calculus. I don't know, are you doing math or bio? You're doing bio, right?
I'm doing
So,
biology.
yeah, so when you go to the university level, you have to think about so many various variables at the same time. Here, our things are very simple. We simplify a lot. So there are so many assumptions as well. They're clear,
Yeah, okay,
right?
so I had
Okay,
another
very good
question.
question. Yeah,
If the
please do.
upthrust was actually greater than the weight, wouldn't it be like a negative acceleration?
Exactly. But then what happens, Minika, is that we have to change these two. We have to flip. That's the only thing we have to do. Rho liquid minus rho. That's the only thing we have to
Okay.
flip. See, that's the only thing that's going to change, right? Because
Yeah.
now it becomes what then? What are the terms then? If it's going up, where's the viscous force going to be downwards, right?
Yeah.
So then you have this one, U upwards, mg downwards, viscous force, right? And then U minus mg minus F is ma. Then when you do the same thing, actually when the acceleration is 0, what happens? U minus mg becomes equal to F. So based on this is U minus mg now. Earlier we got mg minus U. Understood? So then we have to, only thing that we have to change around is what? Rho minus rho liquid.
Okay.
Very good.
So I was
Good
just
question.
wondering, like, if it was like actual equation, you'd have to have two equations for when the upthrust is greater and for the one for the weight is greater because the density increases when you go higher.
That is a complex situation, right? If you have variations, but it all depends upon the net result. All the values of all the forces, right? We don't know the behavior of all the forces at that instant, because there
Okay.
might be a velocity that encourages what? The viscous force, no? We don't know, right? So we have to think about all the scenarios at once. I will do a question about the person who's going to land from a parachute, right? Then you will understand about the complexity a lot, right? So we are going to connect that thing to what? This lesson. Okay? Right. Okay. So far so good, right, everybody?
Yeah, so
Yes.
if we used a fluid with non-uniform viscosity, how would
Yeah,
the
then
sphere behave?
you can't solve such questions using this equation, right?
Hmm.
Because then that also becomes a variable. Then we have to use higher mathematics. You all only can change one or two variables at a time. No? You all can't change
Hmm.
everything at the same time. You all can't do that in your capacity, because then you all have to use higher mathematics. Okay?
Okay.
So
Okay.
that's but we are simplifying that in what? A-level physics. So now what are the assumptions what are the conditions for Stokes' law? That's what I was going to come to. Conditions for what? Stokes' law.
It's going to have uniform viscosity.
Yeah, all that has to be there. And also the laminar flow has to be there. There has to be laminar flow, right? And also, what can we say? Fluid should be a Newtonian fluid with constant viscosity, right? Fluid should be what? Fluid should possess what?
Like it does not, like it mustn't change, like it doesn't change with velocity or time, right?
No, right? It is what we call a Newtonian, what? Newtonian fluid, right?
So what exactly does Newtonian imply, sir?
Newton is associated actually with these laws. He's there again here,
Oh.
right? So then with that connection with the scientist, we associate that, right? So we say Newton's laws of motion. So as long as he's connected, we pronounce that, right? Okay, so I want you all to do a small exercise now. I want you all to try this out. I want you all to plot the variation of the acceleration of the sphere with time, the velocity of the sphere with time. So I will just make this smaller. With time, and I want you all to plot the displacement with time, right? Could you all do that? Or should I explain that? I think you all don't have the note, right? Is it difficult without the note?
So if you just wrote the equation on the side, might be able to plot the graph.
Okay. So equation, but then there are so many scenarios, Minika. But so mg, acceleration equals mg minus up plus minus what? Viscous force divided by mass m. You can just draw a sphere and think about it, right? Just give it a try, right? So you know now, initially the acceleration is maximum, right? We saw that. Why? Because there was no viscous force. Initially, there was no viscous force, therefore the acceleration was maximum. But can you see, as the viscous force keeps on increasing, we talked about the viscous force keeping on increasing, right? Am I recording this?
Yes, sir.
Yeah. So, yeah, the acceleration downwards is decreasing, but the viscous force keeps on what? Increasing. So what happens is, overall the acceleration decreases, right? But in a non-linear pattern, because you can't see any linearity in that equation, right? See? What's that equation? mg minus u minus f over m equals acceleration. So when the viscous force increases, acceleration decreases, right? So there's no linear fashion in which it decreases. So what can we say then? Now, maximum is at the origin and the acceleration decreases, right? So, and eventually reaches what? 0, right? This is the terminal velocity at that point, right? This is the time in which there's a terminal velocity. Is that okay? Did you all get this graph?
I got it wrong, sir.
It's okay. You're learning.
Yes, my
Mm.
one was correct.
Okay.
As
So
I
Unico is
said, the
correct, right?
acceleration becomes 0 at last. So can I tell about the velocity graph also? Where the velocity is starting at 0, it's rising because the sphere accelerates downward, and as the opposing force grows, the acceleration is decreasing. So the
Yeah.
velocity still increases but more slowly until it reaches a constant terminal velocity. Correct,
Brilliant.
right?
Brilliant.
Yes,
Yeah.
okay.
So what
So
happens
it's
is now we can see
eventually gonna get flat, right?
it's going to get flat. Exactly. So
Mm.
you don't have to think anything else. Actually, you can look at the graph. Like, I mean, anyway, acceleration is decreasing. Now. If the acceleration decreases, you know, the gradient of the velocity time graph gives you what? Acceleration, right? If the acceleration decreases, that means what? The gradient of the velocity time graph has to what? Has to what?
Decrease.
Yeah,
Decrease.
decrease. Yeah, exactly. So, but you're starting with a 0 velocity, right? So
Mm.
then the acceleration keeps on decreasing. Therefore, the gradient of the velocity time graph keeps on decreasing, and eventually, when the acceleration becomes 0, what should happen? There should be a flat line because
Mm.
the gradient becomes 0 for the VT graph when the acceleration becomes 0. This is what we call
0.
the reaching of what? The terminal velocity. Terminal velocity, right? Okay. And what about displacement? See, the area keeps on what? Increasing.
Mm.
See, the amount by which the area increases every second keeps on what? Increasing. You know, the area under the velocity time graph gives you what? Displacement. So
Mm.
every second the area increases. That means every second the displacement increases. That means in the next second the displacement increases more than the previous second. The amount by which the area increases every second increases. Is that clear? Right?
Yes.
The amount by which the area increases every second increases. That means the displacement increases happily. Right? There's this encouraging increase of what? Displacement. Okay?
Displacement.
And if you look at the final point, what can we say? If you look at it, the area remains constant,
Mm.
right? So which means the amount by which the displacement increases stays the same. That means the displacement increases the same amount every second, right? So when you go from A to B to C, when you go from A to B, what can you say? There's an encouraging increase of what? Displacement. But, so it's a curve, right? It's potential. Like, and then after you reach point B, what happens?
Straight.
Because you can confirm this. How can you confirm this? Basically, how you confirm this is if you take the gradient of this graph, what's that equal to? Velocity. The gradient of a displacement time graph is equal to velocity. So what happens then? The gradient here is constant, right? In the B to C region, the gradient is constant. Therefore, the velocity is also constant, right? So you can always compare these things. Comparison helps you to what? Confirm your answers, right? So that is how you solve that question, right? So, so yeah, that is the end of like 2 parts of what? Viscosity. I think we should better start the next part the next day, right? There's only one tiny part. We can start off with that part and also solve some questions. I can give you some homework, right? I'll send a tune that has questions. You all can try some questions that I have highlighted, and we can discuss those questions in the class. Other questions you all have to solve on your own, right? And if you all have any hard questions, let me know early. Maybe I can make a YouTube video or something to upload it, right? So y'all can copy the notes at home, right? So
Yes.
I will share the PDF so that you can copy the note at home. Right?
Okay.
I
Okay,
think
sir.
so. Let me see your last time. And also you all are free to turn on your cameras or turn on your mics or anything you like. It's totally up to you all. Right? So if you all are shy to be seen on YouTube or something, you don't have to but turn on the videos, but of course you can speak, right? So I hope others will also be able to see the lecture.
Hopefully.
Hopefully, yeah. Let's see.
So my lighting is very bad, but I'm just gonna, for the sake of turning it on, I'm just gonna turn it on.
Yeah. Right. So how is everybody? Did you all understand the lesson?
Yes, I'm all right.
Everybody's fine, right? So
Yes, sir. This side it's crystal clear. The lesson. It was very clear. Thank you so much for first of all arranging this session and
Yeah.
yeah,
giving us the freedom. It was literally like a playground today. We just I mean
With
okay.
like other kids.
yeah, like we just got the freedom to, bring out our opinions, ask our doubts and all that. And you even took time, you were patient with us and you cleared out everything.
Yeah.
And yeah, sir. Thank you so
If you
much.
are happy that I'm happy to continue, right? In the sense, all I need is this energy, this vitality,
Yes.
right? Because as a
Yeah.
society, I just spread this message. As a society, everybody has a role to contribute, right? So when we change, the world changes. And we have to face the world, right? See, the people who are transforming the world are the people who face the world. Have you all seen? Who communicate, and you have to be communicators. For example, Professor Brian Cox, he communicates with the world, right? And so, and also about studying, whatever that's done in the class, then and there you have to finish it though.
Yes,
Exactly, I'll
sir.
turn this video, all right? Whatever that's done in the class, then and there you have to finish it off. Like today itself, we can finish it. Oh, because what happens is you remember everything that I taught you, right? You do remember everything that I taught you. So then you can modify the note. Then you can see something else about viscosity. Research it, right? Go through the YouTube, and then go through some articles, read about viscosity if you all have time. And now you can solve some questions on your own with the theory that I've discussed. So you have the base of the books, you can do it. And always remember, this lesson is your target. Think of this lesson as a lesson that purchases you some marks. For example, viscosity lesson gives you like an essay question, 7.5 marks. If it comes, right? And if it comes as a practical, another 5 marks. If it is an MCQ set of questions, maybe 1 mark from viscosity or 2, right? So you are getting marks from this lesson. So you have to think, okay, I'm finishing this particular lesson to score for the exam. And your final goal should be the final exam, right? Nothing else. So the fact is the final exam. So you should be working for that particular fact, right? So after doing this lesson, you can write the note down, teach yourself, right? Or teach a friend or something, any other means, right? Be very proactive, be vital in the process of learning. And that is what helps you to be studying freely with a sense of freedom. And be free, as human beings, because to me, there's no difference between the teacher and the student. I'm always telling you. To me, everybody's the same. Is that clear? To me, everybody is the same. Right? I don't have any divisions. And we should not have any divisions. Right? So then it's easy to have a conversation, right? And to be able to learn. And the ones who are listening to this, it doesn't matter. I'm not asking you all to talk by force, right? It's your choice to talk. The ones who are going to talk can what? Talk, right? The ones who don't feel like talking, y'all can listen to the lecture and get something right from the lecture. That clear? So that's it. So next day, I'll send a tute that has questions. Solve those questions and do some questions from Pesru as well. I'll select some questions and do them. And then once we discuss that, we can go on to the last part of viscosity, and maybe we can start Young's modulus or something next day. Right? Okay. then thank you for listening, right? I will see you all next day. Right?
Thank you, sir.
Okay.
Thank you,
You're
sir.
welcome.
Thank you
Okay.
so much, sir. The
Goodbye.
session was fruitful.
Okay,
Really
I'm
Yes,
happy.
fruitful.
very much.
Okay, I'm happy, right? Yeah, I was very happy.
Yes, sir.
Okay,
So I'll
see you.
see you tomorrow.
See you, right?
Yeah,
See you
sir.
tomorrow.
Yeah.
Bye, sir.
Good night, sir.
Take care.
Thank you.
See you all. Right, bye.
Bye,
Bye.
everybody.
Okay.
Bye. Yeah.
Bye, bye.
Okay.
Bye, everybody. It was nice to meet you all. Bye.
Yeah, y'all too.